Welcome, everyone. Thank you for attending today's SDL webinar, Communication Basics Part 1. Before we get started, I'd like to bring a few items to your attention. This is an audio-only broadcast, so all participants are muted. Today's webinar will be 2 hours long, including questions at the end of the presentation. There will be a recording, which will be available on our website very soon. If you have any questions throughout the presentation, please submit them through the All Panelists with the Q&A tool at the bottom right-hand corner of our application. Any questions that are not addressed during the live event will be answered by our presenters via email. We will also be offering PDH credits for participants in today's live event. To receive PDH credits, you must attend at least 75% of the webinar, and no partial credits will be awarded. You will receive your certificate via email. Our first presenter today is Anthony Leon. Anthony is an automation application engineer based out of our Phoenix, Arizona office. My name is Chad Garrison, and I'm an associate communication application engineer located in our Lakewood, Colorado office. Today, I have the pleasure of presenting with Anthony, and we'll both be answering questions. Now, I'll pass the microphone off to Anthony.
Okay, thank you, Chad, and thank you everyone for attending today's webinar. I appreciate you taking the time out of your day to attend this presentation. Before I introduce today what we're going to be talking about, I'd like to remind everyone that we will be presenting part 2 of this series tomorrow at the same time. And if you need a link to that presentation, or if any questions come up during this presentation, again, I want to remind you to submit those questions using the Q&A tool at the bottom right corner of your WebEx application. Okay, so today we're going to be covering serial communications. I'll be covering the serial communications, both RS-232 and 485. We're going to talk about cabling and pinouts and the standards. We're also going to talk about, Chad's going to take over and talk about fiber optics and Ethernet. And then tomorrow, Wellington and Scott will be talking about SCADA and peer-to-peer protocols and communications architectures. Okay, so with that, let's go ahead and get into the content of our presentation. So serial communications, it's just, the slide, we say it's the simplest form of communication between two devices. We show 3 different, flavors of serial communications. The first one, I haven't run into this one, and this is more for simpler devices. It's the simplex communications. And it's a one-way communications path only supported by very simple communications networks. So I haven't run into too many devices where this has been the scenario, but what you'll probably overwhelmingly run into is either a half duplex scenario or a full duplex scenario. So half duplex, basically what this diagram is representing is on the left there would be a device that has a transmitter and a receiver. And on the right, there's a device that has a transmitter and receiver. And what they're doing is they're sharing that communications channel in between, which requires the transmitter, whenever the device on the left needs to transmit, it will turn on its transmitter and transmit its message out onto the communications path. And meanwhile, the device on the right should always have its receiver on, unless it's going to go ahead and respond to that message, and at that point it will turn its receiver off after it's received the message and turn its transmitter on and respond back to that message. So basically, the switching of the turning on and off of these internal transmitters and receivers inside the devices, the timing becomes very important in a shared communications line like this, in this half duplex situation. In the full duplex communications, we basically are providing a 2-way communications path with independent data channels so that each device is free to transmit and receive simultaneously. This is assuming that the devices do support that type of communications. Full duplex, as an example, just to give it some context, that's required for our mirror bits communications protocols that we're going to talk about tomorrow. And so basically that requires the 2 devices to be able to be both sending and receiving data simultaneously. So we're going to start out by talking about 232 or EIA 232, or it's probably more common that I always hear people say RS-232. So it started out as RS-232, and then the standard or the specification was revised by the Electronic Industries Association, and so now it's referred to as EIA 232. But the general practice, it's the general rules of thumb to remember is you don't want to go, generally speaking, longer than 15 meters or 50 feet over copper medium. You can go much further over fiber optics, but when we're talking about 232 communications over copper media, we're talking about 50 feet limitation. That's what we recommend. Okay. And then the standard doesn't define the protocols that use 232 communications. These just basically define the physical interface functionality. So protocols are independent of either the serial communications type, whether it be 232 or 485 or 422. So the original RS-232 specification, it denotes the use of this 25-pin cable. So where you'll see that in substations, and generally speaking, I see those on modems. Usually I'll see a 25-pin port on a modem. I'll still see that from time to time. But that's pretty rare on SEL devices. Most of the time you're going to see a DB9 serial port, and that's your more modern 232 devices, including our SEL products. So when we say a DB9 interface, that's the standard, DB9 interface on the back of a relay that you're probably used to. But first, let's take a look at the 232 DB25 wiring or DB25 connector here. You'll see that there's first of all, we're not using all 25 pins. It looks like we're using, 2 through 8. So we have 7, 8, 9, 10, 11 pins we're using. Normally, so you'll see the 2 pins called the synchronous mode transmit clock and synchronous mode receive clock. Those are not used in the SEL relays today for standard 232 communications. Usually we're talking about asynchronous communications when we talk about serial. And these synchronous modes is for synchronous communications, which you're probably not going to run into too much when we're talking about communications to SEL, IEDs, and whatnot. So the other pins, the DTR, DCD, and the DSR, these pins now, the data terminal ready, that stands for data terminal ready, data set ready, and your data carrier detect. Those are typically used for modems to help with the communications. And so we're not going to go too much into modems and these pins, because we're going to focus on the ones that are used by the SEL products and the SEL, our standard SEL relay serial ports. And so those pins are your transmit, receive, request to send, clear to send, your ground, and then your reading indicator, and then, like I said, actually just the RTS, CTS, transmit, receive, and ground. And then you'll see on upcoming slides that the DSR, DCD, and DTR pins have alternate functions for SEL devices. Okay, so here is the 232 DB9 wiring. So this is important to know. From looking at it, you can tell now which pin is which. And typically, you actually will see, actually, let me put my laser on there. I forgot to put that on there. So typically, you will see that it will have this shape, and you'll actually see, if you look real close on the end of these connectors, usually you'll even see a very tiny number inscribed on the back housing here. So you'll see 1, 2, 3, 4, 5. So if you have good eyes, usually you can take a look at that. Otherwise, you can look this up on the internet. But here's the pins, those 9 pins. Again, we didn't bring over the synchronous mode pins because those are rarely used for the communications that we use for SEL equipment. And we're going to go over these pinouts and their uses in detail coming up. Okay, so this is a very fundamental concept to understand with 232 devices. So we have, we have what we call DTE devices and DCE devices. So DTE devices are data terminal equipment. So that'll be things like, the ultra rare built-in serial port that you may have on your computer. Most of the time we have USB ports now, then we use USB to serial converters, but there's still some laptops out there you can get with a DB9 serial port. And then, our SEL relays and meters and other IEDs, they're going to have DTE ports or their DTE devices, and their wiring on those DB9 ports follow the DTE standards. So data communications equipment typically refers to things like modems and radios for like the SEL 3031 or the SEL 9192. So that's our serial radio or our modem. So those are usually DCE devices, and the pinouts on those ports usually follow the DCE conventions that we're going to see, as well as the transceivers. If a transceiver plugs into a DTE port on a relay, it also needs to be this DCE configuration. And don't get too hung up on it now, because we're going to talk about what those two wirings mean, or what the implied wiring means whenever we identify a device as a DTE or a DCE device. Okay. So this is the DTE pinout. So it's really important if you don't know what cable to use, or you don't know what kind of pinout you have on a device, look it up, and you'll see in the manual that you can find the pinout. You'll have what each pin's purpose is used for, and mainly you want to find out first of all if it's a DTE or a DCE device, because if we say it's a DTE device, the wiring, basically it is implied that the wiring will be as such here. So this would be a DTE wiring, and it's also good to have. This is like something that would be good to have on a cheat sheet laying around, so you'll know what the functions of these pins are if it's a DTE device, and then similarly if it's a DCE device, you'll see that there's the function of the pins. You'll see that really there's not a lot of huge differences between DCE and DTE, but we've highlighted pins 2, 3, and 7 and 8 because those are where the differences lie. But this is probably the most this is probably the one thing that gets people when they're first starting out to get hung up on, is that on a DTE device we call this pin 2, that's your receive data, and we call it receive data in, and the transmit data. It kind of seems intuitive that your transmit data would be out in the out direction, and your receive data would be in the in direction. So I always found that it's easier to understand, and I'd say that the DTE configuration is very intuitive when you're first starting out. So transmit pin would transmit data out of that pin, and a receive data would receive data in through this pin. It makes more sense, intuitive sense to me. And then your RTS and CTS pins, we're going to talk about hardware handshaking later, but the thing to keep in mind here is this is an RTS pin that goes out, so it's a request to send, and that's going out, so that makes more sense. And of course, if you're going to get the permission to start transmitting, you get this clear to send signal back in. So it makes sense the direction of these ports. So request to send would be going out, and then clear to send would be going in. And then these, like I said before, the ring indicator, DSR, DTR, and DCD are not used in most SEL, relay serial ports. Those, we have alternate functions that we're going to talk about for those. Okay. So now on the DCE, you'll see with the main difference. So you'll see that pin 2 is still called receive. If I go back and forth real quick, you can kind of see the pins 2 is still called receive data, in both configurations. But one is receive data out and one is receive data in. And again, intuitively, this doesn't really make much sense unless you think about it in the context of what this DCE device is. This DCE device is a communications device, so it's going to be connected to a DTE device, and it's going to be basically relaying the communications from that's coming into that serial port on the modem and sending it to the remote in to a different modem. So, or radio. And so we can say that on the DTE pin, so the easiest way that I found to kind of go through that is just to imagine a message coming from an end device, one of these DTE devices. Let's say it's coming from an RTAC, okay? And we want to, and the RTAC is of course a DTE device, so if we want to send a message to the remote end, there's a relay that's hanging off of a modem out in a substation, and the RTAC in a different location, and it has a modem. What we would do is we'd send out that request for data. We'd send out the data out of the transmit port at the RTAC on this pin 3. And so if we follow that pin 3 right into the modem, you'll see that the transmit data coming into the modem is coming in on pin 3. And you'll see that hopefully that makes more intuitive sense when you're thinking about a device that's going to relay this communications to another communications device. So you'll see that the transmit data is coming in, and it's being relayed to the other remote end, to the other modem, and that other modem would receive that data, either over analog lease lines or whatnot, and it will receive that data and push it out on pin 2, which is the received data, but it's out. So it's the received data from the local end is going to all the way to the remote end. You receive that data and push it out on pin 2, and then the end device, we're going to say it's a relay, has this DTE communications on. So pin 2 on that receive device, or that DTE device, is to receive that data in on pin 2. So we followed basically from the RTAC and went out pin 3 into pin 3 of the first modem, transmit data in, and then of the second modem, now it's received data that it's received, and that comes out of pin 2 and goes into pin 2 on the DTE configured relay. Okay. So the confusing part, though, is if you look at if you go to look and make a cable, you're going to look at that cable and you're going to see that the DTE and DCE devices, they may have the same, where you call it a RX pin or an RX pin, whether it's DTE or DCE, you'll call it an RX pin. And so it can get real confusing. So a lot of times if you're just looking to wire, RX to TX, that might not be a good method if you're not taking into account that the DTE and DCE devices have different pin outs. So it's just something to keep in mind. And we're gonna, and hopefully it'll make more sense too when we talk about some other cabling options here. Okay, so this is the DCE wiring. And again, keep in mind that this wiring here is basically what is implied when you say this is a DCE device. And this wiring here is what is implied when you say you have a DTE device. Okay. So from DTE to DCE communications, like I just spoke of and kind of went through that exercise, is this would basically only requires, so this DTE receives the data on pin 2 and then transmits on pin 3, and then the DCE receives the data on pin 3 and transmits the data on pin 2. Okay. And so you see that these basically can be connected. The transmit of the DTE device can be connected, basically pin 3 can be connected directly to pin 3 on the DCE device, and vice versa. The pin 2 can be connected directly to pin 2. So you don't need to roll your communications. And when I say that, this null modem, this term null modem, if you ever hear this, we're not talking about like a communications modem type of device. We're talking a null modem cable usually refers to a cable that basically, pin 2 on one side is connected to pin 3 on the other, and vice versa. And pin 5 is connected straight across, and then usually pin 7 and 8 are both traded. So pin 7 on one side is connected to pin 8 on the other for hardware handshaking, and vice versa. And so a null modem cable allows for 2 DTE devices to talk to each other, because now they have the same pin out, so we need to roll the transmit to be connected to the receive, and vice versa. And then DCE to DC communications also will have that same requirement. But the nice thing about DTE, a DTE to a DCE comm, so like for our example, the relay and a modem, is that since the pins are rolled in DTE versus DCE wiring, you can use a standard straight through cable where all the pins go straight through, pin 1 to 1, 2 to 2, 3 to 3, 4 to 4, and so on, all the way to pin 9. And you can use that between a DTE and a DCE device, the straight-through cable, because of the way that these ports have been chosen, the pins have been chosen. Okay. All right, and then the SEL-C662 cable, that's our USB to serial cable. I just wanted to remind you that this is a great option, regardless of whether you need to talk to a DTE or DCE device. We actually, the C662 cable, it actually has a dip switch, or let's say a switch on the side of it that lets you select whether or not you want the cable to be in a DTE mode or a DCE mode. So it's fairly convenient to not have to carry around that null modem cable or an adapter that will do that swapping of the transmit and receive pins. You can actually just do it with a flick of a switch. So it's very, very beneficial to use this C662 cable. And just so you know, you can run into trouble using some third-party USB to serial cables. I'll just warn y'all that you can run into some issues if the driver isn't up to date, and basically not every single cable does a good job of converting from USB to serial communications. And keep in mind that also is included in our warranty. The 10-year warranty covers those cables. Okay. So now let's talk about the SEL specific, functions for the individual pins on a DB9 connector. So again, we're talking as a DTE connector, and really, I was thinking about this presentation. Really, the only place I can think of DCE communications would be on devices like modems, radios, and maybe communication equipment, like the Icon. But as far as the relays and RTACs and other devices like meters, they're all DTE devices. And again, the same, the receive data, transmit data, the ground, RTS and CTS and shield, those are all still used just like the standard EIA 232. The only thing that's different is we commandeer these pins 4 and 6 to transmit an IRIG signal. So we transmit the IRIG signal on pin 4, and then the IRIG signal ground is on pin 6. And so that way we can actually perform another function on using the same serial cable. So you can provide a demodulated IRIG input into that device for time synchronization purposes, all using that same serial cable. And we're just making use of some of the pins that are not used because we're typically not going to be using basically we're typically not going to be using those pins 4 and 6 for their original purpose. We're going to be using those, take those over for IRIG-B plus and minus. And then also we have a pin 1 is typically used to provide a 5-volt power. That's used typically for power transceivers, like if you have a fiber optic transceiver that needs to go onto one of these ports, you'll plug it into the port. You can put 5 volts on pin 1, usually through software in the RTAC, or in the relays you may have to put a hardware jumper on the port, and that'll put the 5 volts on pin 1, and our transceivers and other devices can use that as a power supply. Okay. So these are the typical SEL pins for DTE DB9 connector. Okay, so let's talk about hardware handshaking. So this concept this one is actually also, again, a pretty confusing concept because a lot of people think of hardware handshaking or handshaking. They're not really clear that there's two different, completely different methods of hardware handshaking. One would be software handshaking, and one would be hardware handshaking. Okay, so the traditional hardware flow control, that would be the hardware handshaking, basically uses those two serial port signal lines, your pins 7 and 8, to transmit. So basically, if the one device needs to transmit onto to the comm network, basically it'll assert its RTS pin, the request to send. So basically, it's asking the remote in if it can send traffic or send data over the line. And the other end will receive that on the CTS pin, and it will go ahead and grant permission by asserting its RTS pin, which is wired to the local CTS pin. So basically, you've raised the RTS pin on one side, it raises the CTS on the remote side. That remote in device decides if it's ready to receive data, and then if it is, then it will assert its RTS pin, which in turn asserts the CTS pin back at the local side. That gives that first device the go-ahead that it's okay to start transmitting. And if those conditions ever change, that remote in device can go ahead and deassert its RTS pin. Therefore, on the local side, it will get that signal and interpret that as, okay, I need to stop putting data out on to the comm channel until I get that that CTS pin locally goes back high. Okay, so it's using those two pins on each side to basically control the flow of data. And that usually comes into play whenever you have the sender and receiver can't always process the data at the same rate, and so it can use those pins as a mechanism to control the data flow. Now, software flow control, this is used by SEL extensively in our SEL protocol, and it's used widely in other places too. But instead of using these two pins to control the flow of data, you're actually sending characters. This X-on character and X-off character. And if you've never heard of an X-on, X-off character, don't feel bad. I don't think I had either. But basically, it's there's all these ASCII characters you can send. You're used to all the ASCII letters, letters, numbers. Basically, there's a character for each one of these. And X-on, X-off happens to be you can send an X-on using Control Q and X off using a Control S. So that's how you would use a keyboard to send these over the line. But typically that's not what happens. The devices basically handle the X on and X off characters just in the same manner as RTS, CTS to control the flow of data. So basically this is a little different because it's actually those characters are mixed in with the data. So whenever it sees that X off character, it's going to actually stop transmitting. A device will stop transmitting until it now receives an X-on character from the remote end. So it's two different considerations, and the important thing to remember is that if you have X-on, X-off, enabled on the relay, and then you should also have it on, enabled, in the device that's talking to the relay if you really want to make full use of that X-on, X-off handshaking. And that goes for RTS as well. If you want to enable RTS and CTS handshaking in the relay, then you also want to make sure that you're doing that in the RTAC or whatever device is talking to it as well. Okay. So yes, that's good. And then again, this is important to consider. When the transmission medium requires careful timing. For example, they show here is wireless radios, but that also can come into play. Back from that one of our first slides there. When we have our half duplex communication, those timing can be very, very important to consider the timing in a half duplex scenario because whether how those devices turn their transmitters on and off really needs to happen at the right moment in time. Otherwise, you can miss characters in a message, and then you haven't preserved the data integrity and failed your communications. Okay. That being said, I will say that if you're not using hardware handshaking, or if you are using hardware handshaking, that's great. You can use there's settings for you can add in delays and things of that nature. But if you're not using hardware handshaking, basically if you're not using the right cable, and we're going to talk about that in an upcoming slide, then you really don't want to basically you don't want to tweak those timings if you're not even using hardware handshaking, if that makes sense. It's important to know if you're using hardware handshaking, software handshaking, or both. Okay, so on our DTE to DC communications, we talked about it. Basically, all it's needed is a straight-through serial cable because the SCL-C285 cable basically passes, the pin 2 is wired directly to pin 2 on the other remote end. So this would be like our RXD in, and this would be like our RXD out, and this would be like our TXD out, and this would be like our TXD in pin. And the same with the RTS and CTS. Okay. So this would be the RTS out, and this would be the RTS in, and this would be the CTS in, and that would be the CTS out. And again, this straight-through serial cable, you can find these, usually you can find those things lying around anywhere. Usually an unmarked cable you'll find laying around usually ends up being a straight-through serial cable, but you don't want to make any assumptions unless you have a cable tester to verify that. Okay, so with DTE to DTE communications, this shows our C273A cable. It's probably one of our most common cables. So 2 DTE devices talking to each other. For example, here, the RTAC or an ultra-rare serial DB9 serial port on a computer over here, maybe talking to a relay over here. And what you're going to get, so from the RTAC talking to a relay over here, now your RTAC can now send, they can still talk to each other with the data, and the pin 2, the RXD pin is wired to the TXD pin on the remote end, and vice versa. And then your iRig signal can be wired straight across to provide the iRig signal across pins 4 and 6, that demodulated iRig signal from the RTAC. And then here's your ground pin that goes straight across, and then your RTS and CTS pins are rolled with the 273A cable. So very common cable. It's really important to know that if you're using some basic communications, and let's just say you have a real simple conversation going between 2 devices, and you only are using pins 2, 3, and 5. And there is no pin 4, 6, 7, or 8 on your serial cable, it's important that you understand that there's no way to send iRig on pins 4 and 6 if those pins 4 and 6 are not wired straight across to the other side. So just keep that in mind. This seems obvious, but you use the wrong cable, you can really shoot yourself in the foot. Okay, so DTE to DTE communications, again, this is the same scenario. We still have 2 DTE devices, but now these 2 devices, they have this RTS, CTS pins loop back on itself on each end. So basically the RTS pin, let's just say this device wants to use hardware handshaking, and it asserts its request to send to ask the other side if it's ready, basically. Instead of this being wired all the way over here to the CTS pin and then it responding back with raising its own RTS pin, and then that raises the CTS pin here, what happens is its own request is basically looped back on itself, and it says, you're clear to send right away. And so what you've done with this cable, without any settings, you've basically disabled hardware handshaking. And so that's really important to know what cable you're using. It's almost as important as all the settings that you have. Okay? And then you'll also notice that there's 2 other pins missing here, and pins 4 and 6 we're not doing iRig here. So this would be a great cable to use for again, mirror bits application that we're going to talk about tomorrow. I think Wellington's talking about that. And then, so you don't want to, basically you want to make sure you have the right cable. Okay, yeah, and mirror bits communications does not, you make use of hardware handshaking. So that's why this pinout is really good, because we're not using hardware handshaking anyway, so we went ahead and looped back these 2 pins back on each other at each end, and then your pins 4 and 6 is not necessary between mirror bits between 2 relays. Let's say if you have 2 relays that are communicating over mirror bits protocol, they're not going to be able to send that iRig signal out. Okay. Okay. So both devices must have the same data rate. That's your baud rate. Pricing, common baud rates, 9600, 192. Real older equipment, you're looking at 1200, 2400, 4800. A lot of older SEL equipment has those as default baud rates. But now most of our stuff is all 9600 for a default baud rate. But that goes 9600 doubles 19,200, 38.4, so 38,400, 57.6, all the way up to 115.2. So that's our max serial port speed, 115,200 bits per second. That's the baud rate. Okay, and in general, the longer serial cables used, the higher data rates become unstable and are not suitable for file transfer. So basically, if you stay within that 9600 to 19.2 baud rate, you're probably not going to run into too many troubles. I always like to say, let's just leave it at 9600. You're not really getting much out of cranking up that baud rate when it comes to the applications that we're doing, typically. Okay, so we're reading common 232 communication port settings. So one thing you've probably already all seen using QuickSet or our QuickSet software to send settings to the relay or something like that of that nature, or just any terminal program that you may use to connect to a device, a serial device. One thing you have to get right is the data rate, the baud rate, that has to match between the two devices, and then the number of data bits in a serial byte, and then the parity bit and a stop bit. Okay, so you're always going to have a start bit in every serial frame, and depending on these settings, you'll have different numbers of data bits, parity bits, or stop bits. And the important thing is to make them match on both ends of the communication. And something to keep in mind here, let me go back here, is that if you don't see any settings listed for any of these, I would say the most common default parameters would be like 9600 baud rate and 8N1. So 8 data bits, no parity bit, and 1 stop bit. You've probably seen 8N1 quite a bit. Okay. All right, so transmitting data, how does it work? So the 232 communications depend on a set timing speed at which both pieces of hardware communicate. So that means that based on the baud rate that they're both set for, and the other serial parameters as far as the start, stop, and parity bits, then basically the device knows when it sees a serial frame come in, how to interpret how long these individual bits should be high or low. And this makes a lot more sense whenever we transition over to this next slide. All right, so this is what a signal looks like on the wire, and so you'll see that basically a mark is the equivalent of like a digital 1, and then a space would be considered basically a digital 0 here. Okay, and so you'll see that the mark, this digital, it's in this digital 1 state, and then as soon as this signal drops to 0, basically the bit goes from a 1 to a 0 here. As soon as this transition occurs, it's able to start looking at this as a start bit, basically. Okay, and then now the device knows that these next, due to the settings, that there's going to be 8 data bits coming. So if you look at these bits here, we have 1, 0, 1, 1, 0, 1, 0, 0, and then you have your stop bit. So that's your 8N. It's an example of an 8N data transmission. So we have a start bit, 8 data bits, no parity bit, and a stop bit. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits in a standard serial frame, or I'd say in the most common serial frame, this 8N1 type of serial frame. Okay. And one thing I just want to put out there, this is another thing that goes against intuition, is that this digital 1 is actually, if you looked up and hooked up an oscilloscope to it, it's actually a negative voltage. So if this graph is here, this is actually a negative voltage going up this way and a positive voltage going down this way. So a 1 would be considered this negative voltage, and then the 0 would be considered as positive voltage, or the space. And if you wanted to, create this, get this square wave and look at it, you could, in theory, if you wanted to look, let's just say this is a typical transmitted frame from one device to the other. So one question I would normally ask is, okay, this is a transmit frame, a typical 232 DTE device. Pins, you have your pin out. Your pin out for the DTE device has your transmit data on pin 3. So basically to measure and get this square wave and to view it like say in an oscilloscope, you basically could attach your leads to pins 3 and pin 5 because that's your transmit pin, and then your pin 5 is your ground. So if you measure the voltage from pin 3 to pin 5, this is what you're going to see on a transmitted message. Okay, so hopefully that makes sense. Okay, so similarly, if I wanted to measure this same type of a voltage on the data coming into the device, what it's receiving, we'd switch the lead from being pin 3 and putting the positive lead on pin 3 and the negative lead on pin 5. We'd have the positive lead on pin 2 and put the negative lead on pin 5. So basically, you're taking your reference. Your reference is that ground, and that's going to be your voltage should be 0. And then the transmit and receive pins are going to have a voltage that you're measuring against that reference. Okay. And I will say that's one of the reasons why on 232 communications that it's not very resilient against it's not really it doesn't have a high immunity to noise because if you introduce the noise on that pin 5, that ground pin, then that really messes up the measurements that you're taking between your transmit and receive pins to ground. And so, it's vulnerable to that noise. So that's why your limitation is about 50 feet on 232 data. And we'll talk next about 485 data and why it is that it's more resilient or more immune to noise. That concludes talking about the 232 communications. What is 485? It's communications interface using balance or differential signal process to support point-to-point, point-to-multipoint, and multiple drop applications. So what does that even mean? I guess that was a mouthful. So the communication interface using balance or differential signal. So what we're talking about with a differential signal here, and I'll show you on the pin, is we're measuring, instead of a signal to ground, we're measuring two signals to each other. And that'll make more sense whenever we look at the pinouts here. So, move forward. So here's the specifications for 485. Most of the time you're going to see, you'll see 485 used because of this, either one of these two reasons. One of the reasons is, sometimes you just need to go a very long distance, longer than 232 comms can provide, so longer than that 50 feet or 15 meters. And you use 485, now you're talking 1,200 meters or up to 4,000 feet. That's almost a mile of distance that you can communicate with this 485. So why is, the question comes to your mind, should come to your mind is, how come we can go 4,000 feet with a 485 communications, and we can only go 50 feet with with your standard 232 communications? And really, the reason, one of the reasons is because we get this twisted pair action right here. So I'll flip to the next screen. When you have a twisted pair, basically the induced or the magnetic field basically is every twist that happens, you're basically canceling out the induced noise current. When you just had a pair of straight cables, now all of those induced noise currents are going to add up, and you're going to get a really noisy signal. So if you twist the pair, if you twist the cables, then basically the induced noise current is going to cancel out. So that's one reason why it can go much further. Another reason is because whenever you're, the other reason is because of this differential mode of operation. And I'm still going to talk about that in an upcoming slide. So the maximum number of devices you can have on a 485 circuit is 32. Chances are you probably won't run into that theoretical maximum, but most I usually see is maybe maximum of 8 or 9 or 10 devices on a string, but that's already that you have to consider that if you have a client or a master device, or let's say you have an RTAC and it's talking to let's say 6 relays that are all multi-drop with 485, and you want to pull information from each one of those relays and they're all sharing that same comm channel, you need to basically pull the first relay, get the response back, pull the second relay, get the response back in a round-robin fashion. So if you need to, if you have 32 devices, you're not going to be able to ask the first device for any more data until you've gone through and asked all 32 devices, and that can take some time. And so you can it can really affect the speed that you can acquire information if you have a lot of devices on a comm channel. Okay, and then here's your baud rates. Again, we don't ever really come even close to some of these baud rates. Like I said, we're usually dealing with 9600 or 192 baud rates. Okay, it shows the voltage levels. Okay, so I'm going to skip this one. We talked about it. The twisted pair does have some noise canceling basically properties. For 4-wire 485, this is basically a full duplex operation. If you remember from the beginning of the presentation, full duplex is you can transmit data simultaneously at the same time that you're receiving data, okay, and processing that. So 4-wire cabling, here's the standard cabling. You'll see that TX plus at the master is wired to RX plus at the slaves or the server devices. And TX minus is wired to RX minus, and vice versa. Okay. So typically, only the last device in the chain connects the shield ground wire here. So this shows the shield connected on both ends, but typically what you'll see is that this wire will be landed at the very last device, the shield, and it won't be landed anywhere else. And this is typically a shield. So this is basically on the cable, on your serial cable. If you have a shielded cable, it basically has a metal encasing shield around these conductors. It's almost like, kind of reminds you of like tinfoil if you ever see these cables. So it's almost like they're wrapped in tinfoil all the way around that cable, and at that remote end, there's a connection to that metal or foil. And it's a wire that's landing, and it will land on this ground, and that's a shield ground over here. But keep in mind that this ground is not the same type of it doesn't perform the same function that it does in 232. Remember, in 232 we would measure the voltage from the TX pin to the ground, or to the ground pin, which should be 0. This is not the same. This is the shield is basically connected at the end to basically serve as the shield serves as a Faraday cage for all those conductors that are in the cable. And the Faraday cage is not functional unless you land that shield wire to a ground connection. So basically, that's protecting these 4 wires. Basically, it's also shielding it from more noise. But when you're measuring now, instead of measuring to ground, now we measure. When we're transmitting, we would measure from the TX pin to the TX plus pin to the TX minus pin, and that's how you get your signal. Same with the receive. You would measure the receive plus and the receive minus, and the difference between those voltages. That's how you recreate your signal, and that's why we call it a differential. The mode of communication is a differential, because you're basically able to take the difference between these 2 voltages to recreate your signal. So now think about it. If you have noise introduced on this cable, now the noise will affect the RX minus and RX plus the same, but the difference in those 2 voltages should still be the same, even if they've been offset by some noise. And so that's why this 485 is so resilient. So I hope that makes sense. Is you're measuring a TX plus and an RX plus. You're taking the difference between those 2 voltages, not a TX to ground. I'm sorry, TX plus and a TX minus, not a TX plus to ground or a TX minus to ground. It's TX plus, and you're measuring the difference between these 2 voltages. So it's an important concept to understand. So 2-wire 485, you'll see that only one device can talk at a time, because you'll see that they're sharing. So we have the TX plus is jumper to the RX plus, and the TX minus is jumper to the RX minus. Okay, so let's say when the master is in transmit mode, basically it's going to turn on its transmitter, and it's going to send a signal out across or across the shared comm line from its TX plus to TX minus. It's going to go out, and then after it's done, it's going to turn off its transmitter and turn on its receiver. And when it's receiving the response back, it's going to receive it on the RX plus and RX minus and take the difference of those two voltages. Okay. Again, the half duplex timing is important, because you need to be switching your transmitters and receivers off. If you run into trouble, you can typically add some delays. Maybe you can key up your transmitter and then go ahead and wait a certain amount of time before you transmit the data out across your comm path. And so there's a lot of settings that are associated with those timing, and they become important when you're talking about half duplex communications. Become more important, I should say. Okay. And then as far as termination resistors go, really don't like talking about termination resistors too much, because nowadays a lot of relays and devices end up having termination resistors sometimes built into the devices. So they're less and less commonly used. If you have a 485 network set up and everything is communicating properly, then you probably don't need a termination resistor. And also, one thing that's kind of, if you did have to add a termination resistor to prevent these reflections, if you're having issues, then basically you would connect the plus and minus transmitters. So basically your plus and your minus networks together, and you're connecting them together with this resistor. Where you can find 120 or 150 ohm resistor, when you need it, it better be in your bag, because I don't think you can really run down to the store and get resistors easily nowadays. So if you're going to use this, it may be a good idea to throw one of these in your bag. But from my experience, I'll say that whenever we have communication issues on 485 networks, that's usually one of the first things people want to try out, is put a termination resistor, but it's probably one of the least commonly, it probably is the least common in my experience, to be, the issue has turned out to be usually something other than it needing a termination resistor. So that's all I'm going to say about those. Okay, so as far as converters go, so we have the SEL 2886 that converts 232 to 45 communication. So we have, and there's also third-party devices out there for that also. But for two-wire cabling, it's important to know, for four-wire, it's not a big deal. The full duplex, that translates real nicely to 232 communications. But for two-wire, there's basically two modes. So one mode is you can use the RTS lines, the RTS, basically using your hardware flow control to turn on and off your transmitter and receiver. That's one method. So if you use this method, and you select this on your 2886 with dip switches on your converter, or if you're using the SEL converter, if you're using the third-party converter, this RTS line basically means you're using the RTS CTS handshaking to control your transmitter and receivers. That takes a little bit more, I'd say more skill, less luck, because you can it's going to require those timing to be accurate. If you use the other method, there's this SDC mode. Basically, when it sees a proper serial frame on the 232 port, it's basically going to and by proper, it's going to look at there's dip switches to tell it which baud rate this converter is operating at. And so it sees that proper serial frame coming in on the transmit in pin on this device. it's going to then turn on the transmitter and send that data out. So it's basically more of like a smart mode. And so I would recommend always trying this SCC mode. If you see that, try that out first before you try to do RTS, CTS control, because you'll probably have better luck because it's basically more of a smart mode, and you can pretty much, and it works pretty good. The echo function, this controls a master receive driver. Basically, if you turn on echo, you're going to see your receiver is basically, if you're using 2-wire and you're sharing that comm network, and you turn on and you do a transmit, and you leave, basically if you turn echo on, it's going to leave your receive on, and you're basically going to on your receive in the device, you're going to basically hear and receive all the data that you're transmitting out that was meant for the other end. And so that can cause issues sometimes, one way or another. So depending on the application, you'll want to turn echo on or off. So typically on 4-wire applications, I can turn echo on and it's not a big deal. It works great. And then for 2-wire applications, it's not a good idea to have echo in most cases. Okay, so we talked a lot about 232 and 45 communications. These are all covered. Basically, these are usually, traditionally they're all copper cables, and now we've transitioned into using fiber optic cables for long distance applications, and the technology's improved a lot there. So at this time, this would be a good time for me to hand it over to Chad, and he can pick up where I'm leaving off with fiber optics and run with it.
All right. Thank you, Anthony. So, fiber optics. So, fiber optics actually have a very long history. The French scientist Claude Chappé invented the optical telegraph in 1790s. It was consistent of signals relayed from tower to tower using lights. But however, in the 1800s, it was also replaced by electrical telegraph. Due to atmospheric transmission of light, it was way too problematic for anything more than signaling applications and was typically novel in nature. But in the early 1900s, more optical applications were being developed. These were primarily focused on medical imaging, while patents were filed for communication-based applications. Materials at the time were not able to realize these inventions. The best materials actually had a lot of attenuation or loss of signal intensity properties greater than 1,000 decibels per kilometer. In 1966, though, Dr. Charles Cho and George Hockman of the Standard Telecommunication Laboratories published a paper demonstrating a communication channel of 1 gigabit per second and theorized that the material with attenuation in the tens of decibels per kilometer should be possible. Soon, obviously, the race to develop such materials began. By September of 1970, Corning Glass Works, or now Corning Incorporated, announced the development of a single-mode fiber with attenuation below 20 decibels per kilometer. In the same year, though, the first semiconductor diode laser capable of continuous room temperature operation became available. So the technologies continued to improve at a very rapid pace. And of course, in 1988, Bell Labs installed the very first transatlantic fiber carrying a total of 565 megabits per second on a 2-fiber pair. With the advent of higher wavelength lasers and optical amplifiers, in the 1998 transatlantic cable that was installed reached upwards of 20 gigabits per second with 4 separate wavelengths through a single fiber pair. And then, of course, in 2001, the equipment was available to transmit over 100 separate wavelengths at 10 gigabits per second, each for a total of 1 terabit per second. So what is a fiber optic core, or what is a fiber optic cable? Well, it provides many benefits over alternative technologies. The most application they are used in place is copper or conductive materials to be replaced in electrical transmission data and light transmission. Fiber provides a large bandwidth capacities with much lower attenuation levels than electrical communications. Because the light travels inside the fiber optic cable, it's unaffected by electromagnetic interference, or EMI, making it ideal suited for many applications such as electrical power systems. Along with being immune to the outside source of EMI, fibers do not produce EMI themselves that might interfere with other equipment in the vicinity. So most fiber optic cables are constructed from all dielectric materials that are usually suited for installation in most any electrical environments. Because the fiber optic cable is very compact, lightweight, and very easy to install, it is also feasible and very common to install excess capacity during these initial installation of fibers. Many electric utilities install fiber optic cables inside their power system conductors. With the additional weight and the cost is not very large, but additional fiber provides an invaluable resource even if it's not needed at the time of the installation. And of course, the transmission light does not cause any sparks or electrical arcing or arc flash, even if the cables are broken or damaged. This allows fiber to be used in applications where flammable gases and other safety factors are concerned. So, at the heart of every fiber optic cable is a core. The core is a material that's typically silicon glass, but in some cases made of plastic. The core is surrounded by some form of cladding that has a low reflective index than the core material itself. In terms of refractive index, refers to how fast light travels through a material. So the higher the refractive index, the slower the light moves through that material. This difference in refractive index causes all light to strike in the cladding at an angle greater than some critical angle to be reflected back into the core. Thus, the critical angle is dependent upon the material used and the difference in the refractive indexes. When the light is totally contained and propagates from one end of the fiber to the other, it is known as total internal reflection. This principle was illustrated on a previous optical fiber slide in the very beginning. If you recall, there was that short fiber core with a green light entering the acrylic rod and an internal reflection until it reached the other end of the rod. So, in-step index multimode fibers. So, the core is made out of materials with a uniform refraction index. So as light enters one end of the fiber, it takes many paths to reach the other end of the fiber. These paths are also known as nodes or modes, and they are the source and the destination of multi-mode. Because the light can take many paths and a variety of lengths, not all the light from the pulse reaches the far end of the fiber at the same time. This lengthening of the pulse duration is part of what is known as module dispersion. So significant dead time must be allowed between the light pulses to allow all light to reach out to the opposite end of the fiber. This, of course, limits the attainable bandwidth of a multimode fiber. Light, though, that connects the cladding at an angle greater than the critical angle can escape the actual core and is absorbed by the cladding. So as you can see with the yellow arrows, if the critical angle is too high, it will actually be absorbed by the cladding itself. Now, single mode fibers have an extremely small core that is less than 10 times the wavelength of a transmitted light. At this level, the light propagates can no longer be analyzed by geometric optics like Snell's law. Instead, it follows the differential equations of Maxwell equations of electromagnetism. Single mode fibers also have a smaller difference of the refraction index between the core and the cladding of the materials. Typically, the cladding is a little bit bigger. These factors cause the light to travel through the fibers alongside one path or one mode, hence the designation single mode. Because all light travels along this single path, it reaches the other end of the fiber at the same time, which allows for an increased possible bandwidth. So one thing to take a note in this slide, while the diagram depicts the light as a straight line through the single mode fiber, that is not the case. Light takes a reflected path, but it also follows the same path. So how do I connect fiber optic cables to typically, digital signals? So fiber optic cables can only carry light. Thus, a transmitter must be first created, must create that light based on some type of input signal, like 232 or signal. Depending on the type of the fiber and the application, the transmitter can use light-emitting diodes, or LED, or a laser, a light amplification by stimulation of the emission of radiation. LEDs are typically used in the shorter distance and lower bandwidth applications because they are less expensive. However, LEDs cannot switch on and off fast enough for the high bandwidth application. So necessitating the use of the laser is for those type of applications. Lasers are also typically more capable of higher power output required for longer distance of data transmission, just like the transatlantic fiber. After the light has traveled through the fiber, it must be then sensed by the receiver on the other end. A receiver typically consists of a photodiode and a circuitry to convert the incoming signal from the fiber into a usable output, so a digital signal. The distance and capability of these fiber optics equipment is heavily dependent upon the type of fiber used, the strength, and the transmission device, and the sensitivity of the receiver. So there is dozens of fiber optic cable connectors, but for today, we'll talk about just a few. So many different types of fiber optic cable connectors are still out in the field. New connectors are frequently available, and those already in use tend to fall out of popularity due to new connector types. So in the slide, as you can see from the top left, we have the V-system connectors, or V-pin. They're used for multi-mode applications. They're fast, easy to terminate in the field, and they use a simple click-in design to terminate into the transceiver. Duplex latch kits are available for these applications, requiring latch retention of the connectors to make sure that they don't fall out. Next below that is the lucent connector, or LC, also known as little connectors. They are used in both multi-mode and single-mode applications. They provide latching connectors retention in a very compact package. The LC connector is gaining in popularity to its small size and allows for very dense fiber installations. LC field termination kits are also available. Below that are the ferrule connectors, or FC. They are typically used in a single-mode application. These are screw design, which originally was created for high vibration environments. Back at the top right, we have the straight tip, or ST connectors, also known as the bayonet fiber optic connectors, and they are primarily used for multi-mode applications, but sometimes seen as single-mode applications as well. The bayonet style of the connector provides a quick installation of a latching connector and retention. Below that is the subscriber connectors, or SC, or standard connectors, and they are both used for multi and single-mode applications. Although they have a large installed base, they are beginning to lose popularity, at least in North America, due to the more favorable, more compact LC connector. And of course, last but not least, the mechanical transceiver registered jack, or MTRJ. These connectors were a duplex connector designed to fit in the same space as a phone jack RJ45 connection. They are losing popularity, of course, in for the more favorable, once again, less expensive LC connector. So a couple things to take in consideration when designing a fiber optic system is all the losses of the fiber path that should be considered in weighing against the available transmitter, power, and receiver sensitivity. Additional equipment may be necessary if the loss is too great. Before any installation, I always recommend an optical power budget should be calculated. And of course, fiber optic transceivers encode and decode copper, or EIA 232. The signals of a fiber optic cable are based link, but unfortunately, there are few industry standards for encoding the serial fiber optics connectors. So third-party devices often don't communicate end-to-end on the same fiber optic side of the communication network. The following factors must be considered when selecting fiber optic transceivers for communication links, such as how much available optical link cabling do you have? Is it multi-mode or single mode? The distance of the link, or how much power is required? Same as like IB, rig, transmission equipment. Keep in mind with power requirements, SL relays and other devices provide that 5-volt DC via pin 1 on any standard DB9 connector. Fiber optic transceivers can be plugged directly into the DB9 connector serial port. The transceiver is approximately the size of the DB9 connector shell. So no special mounting is required, no special tools. It's just kind of a plug and play. This transceiver receives power from the host device, once again through that EIA 232 standard connector, and requires no separate power supply or power wiring. No jumping or settings need to really be applied to any SL fiber optic transceiver. So the following is all the different type of fiber optic serial transceivers that SL offers, which can be ordered to match the type, the line length, and the fiber optic in place. Just kind of a few to kind of point out are the SEL 2800, the SEL 2810. Those are both fiber optic transceivers that offer a 650 nanometer multi-mode V-pin connector. They can transmit anywhere from 1 meter to 500 meters, so typically within the same substation. And then also the 2810 offers an iRig-B transmission. Some more popular models are the SEL 2812, the 2814, and the 2815. These are 850 nanometer multi-mode transceivers with that ST connector. Keep in mind that the SEL 2812 and 2814 can transmit between 1 meter to 4 kilometers, and the SEL 2015 can transmit between 2 to 15 kilometers. The SEL 2812 also offers an iRig-B transmission. So, and then of course, one of my favorites is the SEL 2831 fiber optic transceiver, which is a 1550 nanometer single mode transceiver with ST style connectors. It can transmit anywhere from 16 to 110 kilometers in distance. So if you need any type of transceivers or fiber optic communication products, all of this comparison sheet and chart can be found anywhere on our website at selinc.com under the Communications tab. All right, so now we're going to move away from the hardware to kind of discuss Ethernet communications. Because the nature of Ethernet is so robust and a topic to cover, today I'm just going to discuss a little bit about the OSI model, some common Ethernet devices, and of course the physical media in which they interface with. So one thing I always like to point out is what is a network communication? So network communication is a basic concept that follows common rules and a set of parameters. Take, for example, verbal communication. So I, Chad Garrison, am presenting a live webinar on a communication basics to a group of individuals. We need to be able to speak and hear the same language in order to communicate to one another effectively. There might be some interruptions or noise that would necessitate me to repeat myself. And I would also provide a clear signal that I'm done presenting. So computer networking works essentially the same way. It follows a set rule and set parameters for each device on the network and must abide by in order to communicate information effectively. So once again, a network is a collection of two or more elements, such as like computers or people, just for example, linked together for the purpose of sharing information, resources, and more. One of the first computer-based packet switching networks was the Advanced Research Projects Agency Network, or ARPANET, back in 1969. At the time, the United States Department of Defense ran an organization known as the Advanced Research Project Agency, or ARPA. ARPA created the first wide area packet switching network that implemented the TCP/IP protocol suite in later years. And of course, emerging from the ARPANET over the years would be a widespread use of the TCP/IP protocol suite that's still used in today's modern networking of the internet. But as the internet began to gain popularity, the basic internet protocol addressing, or IP address, assigned to each unique machine began to get crowded. So before 1993, IP addresses were divided into 5 categories of classes, or more commonly known as classful addressing. An IP address can be split into 2 sections: the network ID to help identify which network it's associated with, and the host ID to help identify individual hosts. Take, for example, our IP address of 192.168.1.100. The network ID for this address would be 192.168.1, and the host ID would be the last octet of .100. For a classful addressing, this IP address would be considered to be a Class C address because the leading bit of the first octet starts with a 110 in binary, or the 192 in dot decimal. So examples of the classful addressing can be broken down into 5 categories. If the leading bits of the first octet are a 0, this would be classified as a Class A with a total of 16,777,216 possible host address. If the leading bit of the first octet is a 10, this would be considered a Class B with a possible 65,536 host address. And of course, if the leading bit of the first octet is a 110, this would be considered a Class C with only a possible 256 host addresses. And then Class D and E are technically special classical classes, but for the sake of it, let's talk about it. So if the leading bits of the first octet are a 110, this is a Class D, which is reserved for multicasting addresses. And of course, the last class, if E, would be if the first octet are leading by a 1111. And that is reserved for specific reserved special case IP addresses that are typically not used in any IP networking. The classful addressing was the primary networking address method for connecting networks together before subnetting or classless interdomain routing, or CIDR, came along. Imagine just creating and maintaining a global routing table that shows the direct connections between networks and the internet without using any type of CIDR notation or subnetting. We will revisit the IP addressing and subnetting in a little while, but for now, let's examine how Ethernet-enabled devices communicate with one another. The Open Source Systems Interconnect, or OSI model, is the product of the Open Systems Interconnect project at the International Organization of Standards. So a lot of OSIs and ISOs. It is a description and characterizing and the standardizing the functions of a communication system in terms of abstract layers. Similar communication functions were all grouped together into logical layers, and each layer provides services in its upper layers while receiving services from its lower levels below. So if we start looking at the top, we have at the very top, we have the application layer. It manages and programs requests from required access to services provided by a remote system, such as like Telnet or FTP, for example. Below that, we have the presentation layer or translate layer that translates the format of the sender data to the format of the receiver and provides data compression, translation, or encryption. Below that, we have the session layer that provides the connection and negotiation and login to establish and maintain connections and the synchronized dialogue. Below the session layer, we have the transmit layer. This assures kind of the end-to-end reliability. It translates and manages message communications throughout the subnet to ensure data integrity and deals with packet sequencing. Below that, we have the network layer, or the network routing, defines the network segment of the network address scheme, so IP address, and provides connectivity over multiple network segments. It is the foundation on which the upper layers are all based on. Second to the bottom, we have the data link layer, or known as the network interface cards. It creates packet headers and checksum trailers and packetizes the datagrams into frames, detects errors, regulates data flow, and maps hardware addresses. And of course, last but not least, the physical layer of the cables and connectors. It defines the physical and electrical specifications for transmission and defines connector types, pinouts, voltages, and current. So the two layers of the OSO model at the bottom are the interest for most Ethernet and physical layer and the data link layer. Within the data link layer is the medium access control, or MAC, and the logic link control, LLC. These are sub-layers of the data link layer. The MAC layer defines the protocol used to arbitrate access to the Ethernet system. It must be applied to all Ethernet interfaces that appropriate in the original half duplex mode. And of course, the LLC layer provides a mechanism to identify data carried on the Ethernet frame. And then below that, in the physical layer, we have a physical signaling at the physical layer defines electrical structure, so like modulation of the data that moves on the actual Ethernet network. And of course, with that, we also have the media specifications that define the detailed requirements of the media, such as voltage levels, connector types, cables, and so on. So taking a closer look at the MAC layer, or MAC sublayer, we have the first 24 bits of the MAC address that are reserved for the Organizational Unique Identifier, or OUI, which of course is assigned to each organization that builds network and facing devices, thus allowing the manufacturer or the vendor of the Ethernet equipment to provide a unique address for each interface. The manufacturers assign at least 24 bits to a unique address, and the 48 bits are called a MAC address because this represents the address that has been assigned to it on a specific Ethernet interface. So the physical connection, the physical device is the MAC address. And as you can see, there is the one bit that's part of the address field that indicates whether the frame is being sent out or from an individual, such as a unicast or a group multicast address. For individual addresses, the bit is set to a 0, whereas if the bit is set to a 1, we know that that is a group address. Looking at a standard Ethernet frame, the minimum Ethernet frame length is 64 bytes, including kind of the 8-byte preamble. The maximum Ethernet frame size is 1,588 bytes. The source and destination addresses, the type and the length, and the frame check sequence, or FCS, take up another 18 bytes in total, leaving only 46 to 1,500 bytes of data. Ethernet frames include the following type of components. The preamble up front. It's a signal startup time used to recognize that the frame is being transmitted. So because each station on a network has its own oscillating clock, all the communication stations must synchronize their clocks together. The preamble consists of 8 bytes of alternating ones and zeros and ending with 1, 1. The network station is used preamble clock to lock onto the sending station's clock signal, if that makes any sense. For fast Ethernet or gigabit Ethernet, though, it uses constant signaling, thus the preamble is kind of needless, but it's still included to avoid any type of making any changes to that standard Ethernet frame structure. After that, we have the start of the frame delimiter, or the SFD, which indicates the beginning of the frame. Right after that, we have the source and destination addresses. These are each 40 bits in length. And then after that, we have the type and length. The type is a 2-byte field used in the original Ethernet frame, whereas the length is a 2-byte field used in the standard IEEE 802.3. The Ethernet frame is used to identify the length of the data field itself. And of course, finally, we get to the data, which is the actual data payload that can vary from 46 to 1,500 bytes. And of course, at the very end is the frame check sequence, or the FCS. It's a 32-bit field that provides a check of the integrity of the data in the entire frame. So a cyclical redundancy check, or CRC, is a unique number that is generated by applying a polynomial to a pattern of bits that make up that frame. The same polynomial then is used to generate another checksum at the receiving end of the station. So if the two CRCs agree, we know that the data message has been accepted and is valid. The Internet Protocol addresses, or IP address, as we touched before, are used with a subnet mask that defines the device location on the network. IP addressing is responsible for how packets of data are moved from one node to another. The IP address for each packet based on a 4-bit destination IP address. So for example, the InterNIC, or the Internet Registry, assigns a range of IP addresses from different organizations. IP operates on a gateway machines that move data from one network to another. And then, of course, looking at ports and sockets is the name given to a logical port assigned with the Transmission Control Protocol, or TCP, connection. Typically, once a remote device has established that TCP link to a particular socket, another device can no longer connect to the same device on the same socket. Ethernet structures allows theoretical support up to 65,535 sockets per device. So looking a little bit closer at what is IPv4 addressing. So IPv4 addressing are a 32-bit long number made up of 4 octets that contain 8 bytes each. And each octet is normally described in a dot decimal number that is easy to read. 8 bytes of data, or 1 bit, 8 bits of data, or 1 byte, is a single octet that can represent all decimal numbers from 0 to 255. So why 0 to 255? If we write out the number 255 in an 8-bit binary format, each bit would be represented by ones. And of course, if we can convert 0 into an 8-bit binary form, each bit would be represented by all zeros. So take the example of 192.168.77.77. That is a valid IP address because it's within that range of 0 to 255. But if we have 192.168.456.789, that would not be a valid IP address because the numbers are too large than what can be represented in 8 bits. And of course, subnetting is the process of taking a large network and splitting up into many individual or smaller subnetworks or subnets. A subnet mask is a 32-bit number that is normally written out as 4 octets in a dot decimal form. The actual mask, so all the bits that are turned on are represented by ones, tell us what to ignore and what to keep. So if all the bits are turned off, represented by zeros, when we go to compute the network ID, for example, our IP address of 192.168.1.100 and the subnet mask of 255.255.255.0, if we apply that AND operator to binary strings, we have 192.168.1.0 as the network ID. So remember, this subnet mask determines how many hosts can be addressed in a single subnet before a gateway is required to connect to another network. Remember, the IP addresses belong to the networks and not to the devices attached to those networks. A common form of writing an IP address and subnet mask in shorthand is the CIDR notation. Typically, the IP address will be followed by a slash followed by the CIDR number. Our example IP address of 192.168.1.100 has a subnet mask of 255.255.255.0 would be written out as 192.168.1.100/24. That 24 represents the number of bits turned on in the subnet mask starting from the first octet and is categorized as a Class C network, although classes aren't often used anymore in subnet masking. But for knowledge base, a Class B would be represented by a /16, and a Class A would be written by a /8. Looking at transmission protocol again, or TCP, it's responsible for verifying the correct delivery of data between a client and server applications and lives in the transport layer of the OSI model. So TCP provides support to detect errors or lost data and to trigger retransmission until the data message is 100% correct and completely received. TCP links are connected orientated, meaning that the connection is established and held until all the communication cease. Because of the additional overhead associated with TCP, bandwidth resources are consumed by error checking and excessive message acknowledgments. Compare that to with UDP, or User Datagram Protocol, relies on a more simpler protocol transmission method with no handshaking, no error checking, or between the server and the client applications. And just like TCP, it lives on the transport layer. So UDP provides a broadcast mechanism where data packets are sent out on an Ethernet network, but no error checking or validation is done on whether the data arrived to the destination. So UDP typically relies on higher level layers of the OSI model stack, such as the application layer, to detect whether if retransmission of the data is needed or not. UDP-style communications are used for applications where precise timing is required, and some extra overhead on the TCP can make the message less deterministic. So how do we connect our Ethernet-enabled devices, and how do we use the OSI model to talk to one another? So a little history. So back in 1989, Ethernet started off using coax cables as a medium of connection between Ethernet-enabled devices. Speeds are often very slow, typically in the order of 10 megabits per second for coax cables, and shared resources of the same trunk bus topology were very frequent. Soon, Ethernet began to evolve from a single cable connection between two devices, evolved into a simple devices called Ethernet hubs. So Ethernet hubs are considered a simple multiplexing device that connects all those attached wires electronically or electrically as if they were kind of all soldered together. So they exist at the lowest level of the OS model, the physical layer, acting as a central hub where all data ingress and all data egress is seen. They are very low in cost, but hubs do not increase capacity because they are logically equivalent to a single long cable. The hubs eventually were not very effective because all devices connected to the hub saw all the traffic. This led to the development of the Ethernet bridge. A bridge helped segment the network, but ultimately the Ethernet learning bridge evolved into what is known as a switch. So as networks began to grow, the demand for higher speeds from 10 megabits per second to 100 to even a gig, hubs often became oversaturated. So Ethernet switches are like hubs in the sense that Ethernet cables can be plugged directly into the box and connect network devices together. But switches are intelligent multiplexing devices that contain high-speed backplanes that connect all the ports together logically. So switches, unlike the hub, work on a layer 2 level of the OSI model, the data link layer. It creates a robust solution of forwarding packets of information to destination ports that correspond to the correct devices of the MAC address. So port to port, MAC to MAC. Switches, depending on the manufacturer, provide other functions to manage switches such as collision domain to prevent drop packets. Ethernet switches are also flexible in the sense that they are used to interconnect different Ethernet networks together, kind of like forming a bridge between two separate networks, depending on the physical media, such as copper or fiber. And then within the realms of switches, there are managed switches that provide a portfolio functionality to the network. Port security, by disabling unused ports on the switch, or even creating VLANs or virtual LANs, and priority queues or weighted round robin lists. Managed switches help monitor traffic around the network and can provide a web-based interface or use simple network management protocols such as SNMP to collect and organize information on a managed network. They can also build a redundant network that uses RSTP or Rapid Span Tree Protocol to ensure that some or all the switches have a backup path to follow. So let's kind of slow it down a little bit and let's take a look at more common cables used on the physical layer of the OSI model. Probably most common is going to be the Category 5 or Cat5 cabling that is used for fast Ethernet networks, such as 100 base TX or 1000 base T. Within the Cat5 cabling, there are two twisted pair cable pairs for the 10 base T or the 100 base TX Ethernet connections. There's also 4 twisted cable pairs required for the 1000 base T Ethernet connection. So kind of going back to the 485, twisting pairs helps reduce the noise, the amount of interference between them. Each of the 4 twisted pairs in a Cat5 cable, on average, are about 6 twists per 5 centimeters approximately. These pairs are made from typically a 24-gauge copper wire within the cable itself. Nowadays, Category 6 or Cat6 is a cable standard for gigabit E or gigabit Ethernet, and other network physical layers that are backward compatible to like Cat5, Cat5e, or even Cat3 cables. Compared though with a Cat5 or a Cat6, the Cat6 cable features more stringent specifications for crosstalk and system noise. This cable standard provides better performance, upwards of 250 megahertz, and suitable for 10, 100 fast Ethernet, 1000 base T, 1000 base TX, like gigabit Ethernet, and then also 10 gigabit base. So looking at the fiber optic side, kind of going all the way back, there are several optic Ethernet standards exist, including some of the following. 10 base-FL, or fiber optic link, was widespread use years ago with 10 megabit per second Ethernet. And then there's the 100 base-FX, or fast Ethernet. It's a modern standard for industrial Ethernet, so like IEDs or relays. And then there's the 1000 base-SX and the 1000 base-LX, which are multi-mode and single-mode fiber as gigabit speeds are typically used for uplink between fiber Ethernet devices. Fiber optic Ethernet equipment, such as switches, frequently do not automatically sense the speed of the cable, the connection of the devices, so make sure it's important that the same standard be selected when ordering new equipment. So, for example, if we have a switch that uses 100 base FX ports and an IED that only communicates at 10 base FL, remember the fiber optic link of 10 megabits per second compared to 100 base or 100 megabit per second, this would not work.
Okay, thank you, Chad. We've arrived at the Q&A portion of the webinar. Please remember to submit questions to all panelists with the Q&A tool at the bottom right-hand corner of the application. Okay. While you guys ask some questions, I'd like to bring up some questions that were asked earlier in the presentation that I think everyone probably could benefit from. So one comment was made about I just wanted to reiterate that the 232 communications is usually for point-to-point applications, and then 485 can be either point-to-point or multi-drop applications. So we wanted to reiterate that and make that clear. Someone had asked for some clarification on that. Now the other questions. So we had a question about using fiber optic, basically using two fiber optic 1300 nanometer and 850 nanometer wavelengths, if those will be compatible with each other. And sometimes you can get confused with the core size, because the core size don't necessarily have to match to communicate. But if you have a mismatch in core size, there's going to be a calculation you do to calculate the attenuation that's introduced due to that core size difference. But when we're talking about the wavelength usually can't be different. The wavelength that the light is communicating on. So 1300 nanometer wavelength will not communicate with 850 nanometer optics. And then the follow-up question was about 1300 to 1310 nanometer optics. And Chad, I might want you to help me out here. Typically I've seen the 1300 and 1310, from what I've seen, is sometimes they're used kind of interchangeably. Do you have anything you want to add to that, Chad?
Yeah, so just like what Anthony said before about the 850 and the 650, I believe.
1300 and 850.
1300, sorry. It's going to be the exact same scenario. There is going to be a little bit of attenuation due to the difference in the size of the cores. Obviously, it's more ideal to make sure that your fiber optic cores match, but it's not necessarily the end of the world. So there might be some attenuation there, just with the difference of the size of the cores.
Okay, great. All right, and let's see here. I know we had some more questions that were good. See if we got some new ones coming in here. Okay. Okay, give me a second reading. So we have a question here that says, is there an amplifier for 1550 nanometers single mode when fiber length exceeds 120 kilometer limit? So we don't, SEL does not make amplifiers. Of course, you can, once you reach your 120 kilometer limit, you can put another piece of equipment, another termination. So let's just say that 120 kilometers, there's an icon there, and you would want to add a node there, or maybe add another transceiver there that can basically regenerate that signal. But we don't have an amplifier that SEL makes that I'm aware of. Okay, there was another good question I wanted to make sure and ask for Mr. Castillo. Okay, yeah, so there was a question about, is there any information or code associated with the fiber optic exterior colors? I think Ed initially answered this question in the chat here, but it was basically he said he's only seen, typically, and I agree, I've seen the same thing, is that the single mode I've typically seen use like a yellow color, and the multi-mode I've seen be an orange color. Sometimes I see like a blue, blue multi-mode color, so it can kind of vary. That's just typically what I've seen, so don't use those as absolute references, but there are some things that you can derive from just seeing the color. Now there's some, as far as the codes go, this is my own personal experience. I've seen with the multi-mode fiber that there'll be writing on one of, if there's a pair, like a zip cord fiber where you have a pair that's, that's fastened together with that zip cord. The one of the fibers out of that pair will have the writing on it, and usually it'll somewhere say MM for multi-mode, and then it will, and then the writing is only on one of the fibers. So if you have a real long run and you can't figure out which one's your TX and which one's your RX, you can, what I usually do is I'll look at which one has the writing on it and then go to the other end and see which one has the writing on it, and I know that they're the same cable from end to end. That's just I'm not sure that's an absolute something that you can go off of, but that's been my experience. Let's see here. Any other questions? Please ask away. We'll go ahead and give you guys another minute or two to get some other questions in. Otherwise, we'll cut it a little short today and give you guys back some time. So let's see if there's anything else coming in here. Okay, so how to communicate. Okay, what is the term meant by fiber over Ethernet? I think what we mean is Ethernet over fiber, because you can have fiber optics, and you can basically, using our fiber optic serial transceivers, you can have 232 serial communications or 45 serial communications over fiber. But when we say fiber over Ethernet or Ethernet over fiber, we're talking about actually transmitting Ethernet data over the fiber optics. So the fiber optics themselves can be the same, but you could, depending on what's on the ends, you could be transmitting Ethernet traffic or serial traffic. So hopefully that answers that. Okay, and another one. Older stereos, use ST terminations for fiber optics. I'm not sure about that. Now we're getting into some audio circuits, and I don't really know about that. But all right, what are the main advantages of a switch over a hub? So a hub, you can run into some collisions with all the ports physically connected to each other. Switches, managed switches in particular, have a lot of features that can help as far as VLANs. We can do MAC-based port security. We can do port mirroring. We can do a lot of different things with a managed switch. RSTP algorithms to eliminate rings in a Ethernet network. Those are huge advantages over a managed switch. Okay. Or, I'm sorry, over
I can weigh in on that a little bit. Yeah, so the question was, correct me if I'm wrong, was what's the benefits between using a hub versus a bridge or a switch?
What's the advantages of a switch over a hub?
Okay, yeah, so really, a hub at a basic concept is, remember talking back in the early Ethernet connection days was you had two computers that were essentially connected via cable, just one single cable between those devices to communicate back and forth. The hub basically offered a soldered port solution that works on the physical layer of the OSI model, the very bottom layer. So typically with hubs, each device that is plugged into a port is going to see all traffic coming in to that hub and all traffic going out. So everyone that's plugged into a hub on the physical layer is going to be able to see all the traffic. Obviously, not very secure. You also run into other issues such as domain collision and then that shared resource because everyone has to wait to talk in order to actually share the bandwidth. Now, compare that to a bridge or switch. Those are kind of loose terms. It's more of the terminology or like marketing, but a bridge and a switch both operate on the data link layer. They offer more of a backplane logic that connects all those ports together. So essentially what happens is when data comes in to one port, it gets processed and directed directly out to the appropriate port that's connected to that switch. Very good question.
Thank you. Okay. All right. And okay. So I've had some vendors with. Oh, okay. So I've had some vendors have equipment with multi-mode cables that only need a single fiber, not a transmit and receive. Does SEL offer any similar products? That's a very good question. So for our Ethernet switches and Icon products, you can go and look at our SFP options, the small form pluggable options that you can use, and we have options for our 2730M switch or 2730U switch, our Icons, where we have SFPs that transmit and receive on different light wavelengths using a single fiber. So we do have those options. If you just go to our website and you just search SFP, it's very easy to find that page, and it will tell you which SFPs are compatible with our products in a table form. I can follow up with you too there, Mr. Callahan. Okay. For devices such as reclosers, is Ethernet or serial preferred? Most devices we use are serial, but work with some that are Ethernet. So really, it really depends on the application whether you want to use Ethernet or serial. That decision, whether you're using Ethernet or serial, can limit you as far as protocols can go. So if you choose serial, you're not going to be able to use like an Ethernet protocol like a 61850 goose messaging or something like that. And vice versa, if you use Ethernet, you're not going to be able to use some of our serial protocols like mirror bits. Okay, so when you make that choice, you have to know what you're getting into there. Other thing of the difference between Ethernet and serial is that on a serial connection, again, remember we talked about how we can provide that iRig signal over the serial cable. So that's one thing you can do there. Whereas Ethernet, the time synchronization methods are NTP or PTP. So really, when you say is Ethernet or serial preferred, it really is one of those answers where it depends, and you really need to weigh the pros and cons of each. And I'd be glad to. I'm going to follow up with you on that and see if we can talk about that some more. Chad, can you comment on the OC? On the OC, there's a question about what about OC channels like OC12 or OC192? All the channels we use. Icon product, probably even higher speed channels. He's asking if we cover those in this presentation.
Yeah, so OC is typically referred to for sonnet-based transmission instead of like Ethernet. We didn't really cover multiplexing just because the amount of time, typically our Icon course is typically 3 days. But OC12, OC3, OC48, 96, those are all standards used in sonnet multiplexing. Good question.
Great. Okay, let me just see if I can find, let's try to do one more if I can find a good question. Okay. You know what, I think we're going, let's see. Get any more at the last second? Oh, yeah, we got a lot here. Okay. Bear with me. What are the various software tools typically used for troubleshooting / setup of a substation network, such as Wireshark? Great question, Zach. So Wireshark is a great program it's an Ethernet protocol analyzer. If you use it with our RTAC product, you can actually use it to decode even serial traffic. It's one of our main advantages of using our RTAC. So Wireshark's a great troubleshooting tool inside a substation. The other thing is that the RTAC will capture in Wireshark format. Okay. So we're going to, as far as other tools, troubleshooting tools, as far as software goes, usually terminal programs can sometimes be used to help do some logging of communications, like your QuickSet software. You can use that to log some of the traffic in between your computer and the relays to help you troubleshoot. But a lot of times when we're troubleshooting, a lot of these troubleshooting is based on the knowledge of the serial or Ethernet communications, and moving and trying different things out based on the whatever the application is. Okay. And again, there's a follow-up question about the Ethernet versus serial. So Ethernet used to integrate with other applications such as Team. So again, I'll talk to you a little bit more about that because that requires some more information about your application. Because again, there's pros and cons even when we're talking about other software such as our event collection software, the SEL45 Team software. Do we require a transceiver to pass the data Ethernet over fiber? So the answer is we don't need, the question is, do we require the transceiver to pass the data over, Ethernet data over fiber? And the answer is it depends on what the native port is. So if we have a native fiber optic Ethernet port, then you just hook right into it usually with your LC connectors. If you don't, if you have a situation where you have a copper Ethernet port and a fiber optic, Ethernet coming in, then you'll need a separate device. For us, as far as SEL devices goes, the SEL2725, it's a 5-port Ethernet switch with either single mode or multi-mode fiber optic Ethernet ports, as well as standard copper Ethernet ports that can work as a media converter in some cases where it doesn't need to be extremely high speed. So that can work. Great question. Are there repeaters / amplifiers on transatlantic fibers? I would assume so, but that's a very interesting question. I'll be looking that up afterwards, following up with you. So I think that's all the questions we're going to have time for today. So I'm going to go ahead and we've reached the end of the Q&A portion. I want to remind you, if your question wasn't answered live, and I know there were a few of you guys that I didn't get to answer these questions live, you'll receive an email directly from one of the presenters to follow up with all the questions that were asked. We hope that you've enjoyed today's SEL webinar, and we hope to have you join us tomorrow for part 2 of this 2-day communications basic presentation. To learn more about this topic, please visit our website. And also don't ever hesitate to reach out to your local automation AEs to help out with that. So have a wonderful day. Take care. Thank you.